Q6748. As altitude increases, the indicated airspeed at which a given airplane stalls in a particular configuration will A. Remain the same as at low altitude. B. Decrease as the true airspeed increases. C. Increase because the air density decreases. The correct answer is A. As altitude increases, the indicated airspeed at which a given airplane stalls in a particular configuration will remain the same as at low altitude. Indicated airspeed, IAS, is the airspeed read directly from the aircraft's airspeed indicator. It is a measure of the dynamic pressure of the air flowing around the aircraft, and it is affected by the density of the air. As altitude increases, the density of the air decreases. However, the airspeed indicator measures the dynamic pressure, which is the result of the interaction between the airspeed of the aircraft and the density of the air. Therefore, the indicated airspeed will remain the same for a given airplane's stall speed, regardless of the altitude. It's important to note that while the indicated airspeed remains the same, the true airspeed, TAS, and calibrated airspeed, CAS, will change with altitude due to variations in air density. TAS is the actual speed of the aircraft through the air, and CAS is the indicated airspeed corrected for instrument and installation errors. These airspeed values are used for performance calculations and to ensure the aircraft operates within its safe limits. In summary, the indicated airspeed at which a given airplane stalls in a particular configuration will remain the same as at low altitude, even though the true airspeed and calibrated airspeed may change due to variations in air density at different altitudes. 6535. Which statement is true relating to the factors which produce stalls? A. The critical angle of attack is a function of the degree of bank. B. The stalling angle of attack depends upon the speed of the airflow over the wings. C. The stalling angle of attack is independent of the speed of airflow over the wings. The correct answer is C. The stalling angle of attack refers to the angle at which an aircraft's wing reaches its critical angle of attack and experiences a stall. It is the angle of attack beyond which the airflow over the wing becomes separated, leading to a loss of lift and an increase in drag. The critical angle of attack is the maximum angle of attack at which the wing can still maintain attached airflow and generate lift efficiently. It states that the stalling angle of attack is independent of the speed of airflow over the wings. This statement is true. The stalling angle of attack is primarily determined by the wing's design and characteristics, including its airfoil shape and wing geometry. It is not directly influenced by the speed of airflow over the wings. While changes in airspeed do affect the aerodynamic forces acting on the wing, such as lift and drag, they do not alter the stalling angle of attack itself. Increasing the speed of airflow over the wings can provide additional lift and delay the onset of a stall, but it does not change the angle at which the wing will eventually stall. Similarly, decreasing the speed of airflow over the wings can result in an earlier stall, but again, the stalling angle of attack remains the same. 6536. The critical angle of attack at which a given aircraft stalls is dependent on the A. Gross weight, B. Design of the wing, C. Attitude and airspeed. The correct answer is B. The critical angle of attack at which a given aircraft stalls is dependent on the design of the wing. The critical angle of attack refers to the specific angle of attack at which an aircraft's wing reaches its maximum lift coefficient and experiences a stall. The angle of attack is the angle between the oncoming airflow and the chord line of the wing. The critical angle of attack is determined by various factors, and one of the primary factors is the design of the wing. The design of the wing includes its airfoil shape, wing platform, wing area, wing sweep, and other aerodynamic features. These design elements influence the flow of air over the wing and its ability to generate lift. The shape of the airfoil, in particular, plays a significant role in determining the critical angle of attack. Different airfoil designs have varying stall characteristics, including different critical angles of attack. 6558. Which action will result in a stall? A. Flying at too low an airspeed. B. Raising the aircraft's nose too high. C. Exceeding the critical angle of attack. The correct answer is C, because exceeding the critical angle of attack is the specific condition that leads to a stall. The critical angle of attack is the angle at which the airflow over the wing becomes disrupted and no longer produces enough lift to sustain the aircraft in flight. When the critical angle of attack is exceeded, the smooth airflow separates from the wing's surface, resulting in a sudden loss of lift and a stall. The critical angle of attack is determined by the wing's design and airfoil shape. It is a characteristic of the aircraft's aerodynamic configuration and remains relatively constant regardless of factors such as gross weight or airspeed. The critical angle of attack can vary between different aircraft types based on their wing designs and other aerodynamic considerations. Flying at too low an airspeed can increase the angle of attack, but it is the exceeding of the critical angle of attack that actually leads to a stall. Similarly, raising the aircraft's nose too high can increase the angle of attack, but the critical angle must still be surpassed for a stall to occur. In summary, the specific condition that results in a stall is exceeding the critical angle of attack. This angle is determined by the wing design and airfoil shape of the aircraft and remains constant regardless of factors such as gross weight or airspeed. Flying at too low an airspeed or raising the aircraft's nose too high can contribute to an increased angle of attack, but the critical angle must still be surpassed for a stall to occur. 6511. Which statement is true concerning the aerodynamic conditions which occurred during a spin entry? A. After a full stall, both wings remain in a stalled condition throughout the rotation. B. After a partial stall, the wing that drops remains in a stalled condition while the rising wing regains and continues to produce lift, causing the rotation. C. After a full stall, the wing that drops continues in a stalled condition while the rising wing regains and continues to produce some lift, causing the rotation. The correct answer is C. In a spin, after a full stall, the wing that drops, inside wing, continues to remain in a stalled condition, while the rising wing, outside wing, regains and continues to produce some lift. This difference in lift between the two wings causes the rotation or spinning motion of the aircraft. During a spin entry, the aircraft reaches an excessive angle of attack and enters an uncoordinated flight condition. As the angle of attack increases beyond the critical angle, the smooth airflow over the wings is disrupted, and the wings lose their ability to generate lift effectively. This results in a stall. In a spin, the wing that drops tends to remain in a stalled condition due to the high angle of attack and disrupted airflow. The rising wing, on the other hand, may regain some lift as the angle of attack decreases slightly, but it still produces less lift compared to a fully unstalled wing. The combination of the stalled wing and the partially lifted wing creates an asymmetric lift distribution, causing the aircraft to rotate around its vertical axis. This rotation, combined with the descending flight path, characterizes a spin. Therefore, option C accurately describes the aerodynamic conditions during a spin entry, where the wing that drops remains in a stalled condition while the rising wing regains and continues to produce some lift, causing the rotation.